Hello, everybody. I hope you are doing well. This is the video for lesson 4.4, tangent planes and linear approximations. I'm not sure about you. Do you like approximations? Okay, as a mathematician and maybe as an algebraist topologist, I don't really like approximation. I never liked them. So you learned, approximations in calculus 1, maybe Newton's method. Those belong to the area of mathematics called numerical analysis. Okay, and that's a pretty difficult subject. I really wasn't interested, but sometimes you just don't have any other methods of evaluating or estimating a function except by approximations. And the whole concept is based on linear approximation, linearization of a function, which is basically your tangent plane. So in section 4.4, we learned that those two things, linear approximations and tangent planes, are exactly the same thing. Okay, so that's one thing I want you to learn in this lesson. All right, so let's get started in section 4.4. Section 4.4, linear approximations and tangent planes. So just want to say once more, these two concepts are the same thing. Right? So what do I mean by this? Okay. Let's go ahead and start thinking about, start remembering what you learned about linear approximations. Okay, calculus 1 is always a good starting point for a new lesson in calculus. All right, so let's imagine the function y is equal to f of x. All right, and you pick a point on the x-axis, and let's call it x naught. Okay, so the value of the function is, of course, at this value here, which is similar to this point here, it's f of x naught, right? Right, and then we think of another point. This is f of x naught plus delta x. All right, so the difference in the x coordinates is obviously delta x. Sometimes we call this dx. So for the independent variable, the x, delta x is the same as dx. All right, and then so you see this blue line, which is a tangent line, right? So this is our tangent line. And tangent line is, of course, a linear function because it is a line after all, right? And then here's the important part, the difference here, okay? The difference between this y value and the y value here is called dy, okay? And that dy is called the differential, okay? And that is used to approximate the real difference, which is delta y, okay? And so this is what happens with this. And then of course, the idea is as delta x, which is dx, gets smaller and smaller, right, the delta y gets closer and closer to dy, okay? Because pretty much, and again, I should mention that every curve, every smooth curve, because we were talking about derivatives, every smooth differential curve is almost a line. Does it make sense? Yeah, almost a line if zoomed in enough. So if you just keep focusing on this part here, like this point, and get closer and closer to it. And right now, this delta y and dy seem to be very far, very different numbers, right? Delta y looks like it's twice as big as dy. But as delta x or dx gets closer and closer, that curve can be approximated by that tangent line. Every smooth curve is almost a line if zoomed in enough. Right, and so this is the whole idea of linear approximation. See, the reason we do this is because sometimes we don't have a nice equation for f of x. Now you wonder, I mean, if you have to approximate f of this point x naught plus delta y, x, why don't you just plug in the number? Okay, well, if you can, that's great. If you have the equation for f of x, which you normally do for any sort of an exercise in the calculus class. But if you're actually out there doing science or trying to work on an engineering problem, you may not even have a nice expression for f of x. All you get is a point, the value at this point f of x naught, and the derivative. And in that case, you have no idea what the value of the function nearby x is. And so you do what is called linear approximation. right? So you notice here, the tangent line is exactly the linear approximation, right? I mean, when you try to approximate this function linearly, all you are doing is evaluating the value on the tangent line. So the tangent line is the linear approximation. And that's what I mean. We're going to add a dimension in just a second. Then we will be not talking about tangent lines, but we'll be talking about tangent planes. And they will provide linear approximation. Let's do an example in back in calculus 1 first. If y is equal to x squared, okay, you know that dy dx, which is your f prime, right, is equal to 2x, right? Let's pick, let's just pick a point here. Let's see, this point is 3. And of course, the value of the function is 9, right? So f of 3 is 3 squared, which is 9. And f prime at 3 is equal to 2 times 3, which is 6. All right, so if you take the, well, let's use this line here. If you take this tangent line, the tangent line has the slope of 6, right? So that's your m, right? If you are talking about the linear expression, right? And then you write down the equation of this tangent line. The tangent line will be y minus, I'm using what is called the point slope form of the equation of the line. Remember, y minus 9 is equal to 6 times x minus 3. Okay, y minus 9 is 6x minus 18. Y is equal to 6x minus, and of course you add 9 to it, and so this is your linear, this is your tangent line. Okay, but this is your linear approximation. So for instance, if you didn't know, okay, so use this to approximate, let's say 3.01 square. Okay, how do you, I mean, obviously you can actually take your calculator and put 3.01 and then square it, and that would give you the exact value. But if you can't do this for some reason, or if if these are more complicated, this is a more complicated equation, then you can use this approximation, linear approximation, and say y is, okay, so because this becomes your x, right? And so that's going to be 18.06 minus 9, and you can get your answer. Okay, so here you get 9.06, right? The real value, the actual value is 3.01 square, and that is 9.01, 9.0601, okay? So you can see that these are really, really close to each other, okay? Also, there's another idea called, let's see, dy, this is called the differential. Now, the reason I am reviewing all this is because you will see pretty much exactly the same thing when you add one dimension in our calculus 3 class, right? So dy, the point is dy is the thing that approximates, delta x, the delta y, right? And this dy is f prime at x naught times dx. Now that's pretty obvious because this dx, that's just the slope. This is the run. And the slope is f prime at x naught. And then, of course, dy over dx is f prime at x naught. That's what the derivative is. All right. So the differential can be calculated this way. And so what is this in this particular situation? Well, remember, this was 6, right? And then dx, in this case, this is 0.01 away from the point 3. Okay, so in this case it's 0.01. That's your dx, right? So this is 0.06, and that's the difference between the value 9 at the point, x is equal to 3, and this value here. Okay, so if you add this to, so what I'm saying here is this. So f of x naught plus delta x can be approximated by that linear approximation, sometimes called the linearity, which basically says this is f of x naught plus, and you add the difference, which we estimated by dy, and of course, that is what we just wrote, f prime evaluated at that point times dx, right? Okay, so that's all linear approximation, right? And if you remember this, that's great. This will give you a good foundation on which to build what we are learning. All right, and so now we go to Calc 3. Yes, we have been in Calc 3, but this is just a review of this. And so the point was that this whole linearization or the tangent line gives you a nice approximation. All right, so let's now talk about what happens when you have a function of two variables. Okay, so obviously my graphics are not as good as what you see in the book, but I think this is actually very intuitive, right? So think of a point. We are going to call this x naught, y naught. Okay, so this is a point on the plane, and then of course the function is, evaluated at that point, and so this is f of x naught, y naught. That is your z value, right? And then you can see there's a tangent plane, right? And so imagine the tangent plane, which is just like a little piece of, let's say a tile or something. Okay, think of this as a nice smooth roof, and you can pick a small tile piece and then put it right there at the tangent, so it hits, it touches the round surface right at that point. And so that is our tangent plane. We want to find the equation of this tangent plane, right? And so here's what's happening. Now, let's say this is your plane. This is a horizontal plane, okay? And what we will do is this. Because we know about our fx, which is the derivative in the direction of x, and we know the fy in the direction of y, okay? And imagine that these are the what you see here are those two functions. All right, so I'm going to call this, I'm going to just say, declare this to be 1. Okay, so let's say what happens in the x direction if you go 1 unit, from x naught. And then because of the way we define, the fx and fy, the partials, this will be simply fx, right? So that the rise is fx. Fx divided by 1, of course, is fx. That is the derivative with respect to x. And here, the height of this vector is fy, all right? And then this length is 1. Notice here, right? The tangent plane, which is difficult to draw, so I'm not going to draw this, but the tangent plane that I drew is going to include, let me just say, this is V1 and this is V2. And the point is that the tangent plane contains, oh, by the way, so I have seen many pictures illustrating this in various books, and I have to tell you, many books have the wrong picture, whether either X is going the wrong way or Y is going on the wrong way, or you have a different orientation. And that's because it's really, really hard to visualize this. Okay, so that's my excuse for drawing some ugly pictures. I'm doing my best here. The tangent plane contains both V1 and V2. Okay, now this point, that point is f of x naught, y naught. So it's x naught, y naught, comma, right? That's this point, okay? So in other words, the point I am marking, maybe I should use a different color, maybe this bright, what is that? Turquoise color. That is the same point here, okay? And like I said, I'm not drawing the tangent plane over here, but the tangent plane is the plane that contains both V1 and V2. And this point, x naught, y naught, and then the value of the function at that point, right? And for the ease of notation, let's just call that z naught, okay? So this point is called x naught, y naught, z naught, and so that is our reference point. That's the starting point, okay? And so the question is, what is this tangent plane? Well, if it contains both V1 and V2, notice here V1 can be easily written as 0, 1, Fy, okay? That's the vector. And then V2 is this vector, which is 1 because it's coming, in the direction of x. The first one was coming this way, so it's 0, 1, fx. This one is 1, 0, and then the vertical component is fx. All right, so we get the normal component or normal vector to this tangent plane, which is simply v1 cross v2, right? Let's call this n. And that is equal to, notice here, f1. And then what's the second component? It'll be 0 minus fy, but then remember you have the negative. So it's negative, negative fy. So this is simply fy evaluated, of course, at that point. And then the last one is going to be not 1, but negative 1. Okay, so the tangent plane, we are about ready to come up with an answer to this question. What is the tangent plane? Okay, the tangent plane, here's the equation of the tangent plane. So the tangent plane to z is f of xy at the point x naught, y naught. Okay, so that's what we're trying to write. It's a plane tangent to the surface of f at the point x naught, y naught, z naught. And here's the equation, right? What you have a point, we have the point, which is x naught, y naught, z naught. We have a vector normal to it or perpendicular to it. Do you know how to write the equation of a plane given a point and a normal vector? Of course you do. All right, so this will be fx, right, times what? X minus x naught plus fy. You know what, let me just make it a little more clear, because when I say fx, I mean, I'm not talking about, this is not f of x, f sub x, right? It is f sub x, but it is evaluated, and so I should make it a little more clear, right? So this is f of x evaluated at x naught, y naught, okay? So that's one expression, and it's a one number, like 7 or, whatever, okay? Times x minus x naught plus fy evaluated at the same point, these are just partials, times y minus y naught, then plus negative 1. Okay, where did the negative 1 come from? It came from this picture, okay? And I think you will also see it comes from another good reason, but it's minus z naught is equal to 0, okay? Or if you want a simplified version, it's fx evaluated at that point times x minus x naught plus fy evaluated at that point, y minus y naught. These are product, okay? Minus z naught is equal to 0. Make sure you have this part so that you will actually have an equation. So this is the tangent plane. All right, I will do an example of this in a moment, but I want to get the theory down first, okay? But watch what happens though. I mean, all right, so this, I should stop here and say, yes, this is great. This is one of the results you really need to know. How do you find the equation of a plane tangent to a smooth surface at a particular point? If the surface is the graph of fxy is equal to z, the answer is right here, okay? But if you think about this, that's just delta x. Or dx, same thing, right? This is just dy, right? And so this, let's try to solve this for z minus z naught. You notice here, z minus z naught, okay? So this will be the, what we call a dz, okay? Well, that is equal to fx times dx plus fy times dy. That's pretty straightforward, okay? And that's because, here's a picture of this again. If you are at this point x naught, y naught, okay? And let's say you go a little bit over here and a little bit over here. So now you're at this point. This is x naught plus dx, y naught plus dy. And assume that these are really, really close to each other, okay? And so what happens to the value of the function at this point compared to this point, okay? And that's the difference between the two values, which we call delta z. But the delta z is approximated by dz, right? So this is actually the dz. And so we have the differential, and in this case, because we have multi-dimensional functions, here's a definition, it's not just called the differential, it's called the total differential. Okay, and I'll bring all of these together as we do examples. But total differential is called dz, which is the approximation of delta z. dz is equal to fx evaluated at that point, x naught, y naught, times dx plus fy times dy. And that sort of makes sense because in order to go from here to here, you do a linear approximation in this direction, followed by a linear approximation in that direction, right? And this will give you how much how much z would increase in x direction, and this will tell you how much z will increase in y direction, and you just add them together, and that is your total differential. All right. So so what can you say about this? Delta z can be approximated by dz, which is exactly what this is, fy dy. All right. In other words, linear approximation. Okay, so here's the linear approximation method, and the formula is also true. If z is, no, let's say if x, let me just go ahead and set this up right. If x naught, y naught is, or actually, let's say if xy is close, and again, you have to understand what the word close is. It's reasonably close, where the approximation actually makes sense. If it's close to that reference point, x naught, y naught, and if f is differentiable, then the linear approximation of f, and sometimes it's called the linearization of f, okay, is, and here's the formula. It's f of x, y. Actually, it's L, and then you can say L sub f or something. Okay, that is, you first evaluate this function at x naught, y naught. Okay, that is the value, the actual value of z naught, right? And then you just add the differential. Okay, so this is basically also the same as z naught plus the differential, because all you're doing is just adding that extra part. And so this is f of x naught, y naught, plus, right, you evaluate fx at x naught, y naught, and then you multiply this by x minus x naught. And then you add the y component, which is f sub y, x naught, y naught, times y minus y naught. Okay, now again, this can be written simply as fx dx, and this can be written as fy dy. So you add how much you are going to increase z by in the x direction and in the y direction, and you add that to the original z value, and that is going to give you the linearization. Now notice here, this, okay, so what we're saying is this is your z value, right? This is z naught, okay? So this is exactly the same as what we had here for the equation of the tangent plane. Here's the equation of the tangent plane. And if you look really carefully, I mean, this is the same thing. That is exactly what I have written here. So, and that is very consistent with the fact that this is true also in calculus 1. The tangent plane or tangent line was exactly the linearization of this function f at x naught. All right. So get this concept down, and if you understand these pictures, I think you can do all the problems. Let me give you one question, and then I will let you figure out how to find the tangent plane first, and then we will use that to find our linearization. Here's an example. Find the plane, or find the plane. Yeah, let's say find the plane tangent to, and here's my function, f of xy is equal to 2x squared plus y cubed at this point 1, 1. Okay, so let's see, how does this work? Okay, so you're thinking of this 0.11, okay, and don't worry about the linear approximation right now. We're just looking for, so here's the picture, here's 0.11, right? And we don't know what the graph looks like. Maybe it looks like this, and we're looking for this, the tangent plane, okay? That's all you're doing, right? Now, we have an equation, right? And so you can just plug in the numbers in here. Let's try to find f sub x. Oh, by the way, I think that maybe the first thing we need is this point. What is the value of the function at this point? Okay, because we do need that. That's your z naught. So first, let's find 1, 1. F of 1, 1 is 2 times 1 plus 1 cubed, which is 3. Okay, and so we are looking for a plane tangent to this f at 1, 1, 3, basically. And now we find the partial with respect to x, and that will be 4x, right? And then the partial with respect to y is 3y cubed. And I'm going to use this notation here, meaning I am going to evaluate both of these at 1, 1. So this is 4, and this is 3, okay? You get that? You are now ready, believe it or not, to write down the answer. Okay, because this is for the first coefficient, x minus 1 plus 3y minus 1. And then remember the last one, the last component or the last coefficient is for the z is always negative 1. Okay, where did that come from? It's right there. That's what I said. So the negative 1 is always that last coefficient. So it'll be negative z minus 3 is equal to 0. Okay, there it is. That is the tangent plane. Now, if I were doing this, there's something in me that tells me, hey, I really should simplify this. And I probably will do that. Okay, and then these will cancel. 4x plus 3y minus z minus 4 is equal to 0. And that is the tangent plane. To this, the graph of f of xy, which is 2x squared plus 3y cubed at 1, 1. Okay, so that is the tangent plane. Linearization or linear approximation. For this, all you have to do is to solve this for z, okay? Because it is the same thing, solve for z. That's all you have to do. So then z is equal to 4x plus 3y minus 4, okay? And that's going to give you the linear approximation of this function as long as the x and y are close to, for xy close to 1, 1. Okay, so so for instance, let's say approximate f at 1.01 comma 0.98. Okay, now this point is fairly close to 1, 1. So how do you approximate that? Okay, so here's the approximation. We use this linearization. So this, I should write this L sub f or L sub f, L parentheses f. Sometimes people use this notation. Sometimes they use L sub f. And z is sort of deceptive because we use z to describe this real function, not the approximation. So maybe LF is better. But anyway, this is going to estimate the value, the real value of f close to the 0.11. Okay, you notice here, all you have to do really is to plug in. So L sub f is equal to 4 times 1.01 plus 3. All I'm doing is just plugging in here. Okay? And 0.98 minus 4 is equal to, and then all you have to do is to calculate this. Okay, so the linear approximation gives you the value of 2.98. And here I have actually just paused my recording and calculated the actual value. If you want to calculate the actual value, then you would have to basically use a calculator, right? 1.01 times, well, 2 times 1.01 squared plus 0.98 cubed is equal to this. Of course, this is possible, you know, especially if you have a calculator, it's pretty simple. But again, sometimes you don't have an explicit formula for f, and in that case, you may have to depend on your linear approximation. Notice here, that's fairly close to each other, right? There's yet another way of doing this, which is a little more enlightening, okay? I know we just substituted our x and y, the new x and y values into the linearization equation, which is the tangent plane. But if you want to, there is another, maybe a nice way of doing this. So alternatively, okay, this is something else you can do, and maybe this will be helpful. Remember, f of 1, comma 1 happens to be 3, right? And what we are doing is we are trying to find out f of 1.01 and estimating, or we can say, let's use the same word. We try to approximate f of 1.01 comma 0.98. Okay, that's our question. All right, notice here, this is different from 1 by 0.01. And this is different from 1 by 0.02, but it's negative 0.02, right? So in other words, if you are standing at the 0.11, and if you want to go to the 0.1.01 comma 0.98, you have to go in 0.01 units in the x direction and negative 0.02 units in the y direction, right? Now, remember, dz was fx dx plus fy dy, right? And what was fx at that point? We have that? Yeah, we have fx at that point, which is 4, and fy is 3. So this is 4.01 plus 3 times -0.02. Okay, and that is going to approximate dz, or delta z. Delta z is about, or estimated to be, or approximately this number. Okay, and so you can calculate this. This is 0.04 minus 0.06, right? And that's negative 0.02. So all you have to do really is this thing here is approximately equal to, remember, this is approximately equal to f at 1, 1, that's your z naught, okay, plus dz. What we know, this was 3. And this, now we know this is negative 0.02. So this is 2.98, which is exactly what we found here, of course, right? I mean, that's the same thing. But this is just using a differential in order to estimate the point. Okay, so let's do another problem, and then I will let you figure this next one out. Maybe you can do this on your own, and then you can calculate this next problem. Okay, so here's a practice problem, right? F of xy is x times e to the xy, right? Find the linearization or linear approximation of f, which is basically asking you to find the tangent plane, and solve that for z, and use it to approximate f at this number, or the point very close to 1, 0, which is 0.99, 0.01. Okay, so let's see if you can figure this out. And then when you think you can get the right answer, look in your notes and try to work on this. When you think you got the right answer, come back and we will talk more about this together with a few more topics we need to cover in this section.